Hello everyone. In this video, let us learn about the choice of number of poles for a DC machine design. Now that we have started finding the main dimensions of DC machines like D and L, the next step is we have to identify the number of poles required for a DC machine in the stator portion. Now, if suppose you are using an AC machine, what is the procedure? In case of an AC machine, if you see, we all know the formula. It is 120 F divided by P is nothing but the synchronous speed N. Correct? So if we know the value of the frequency of the machine and if we know the value of the speed of the machine, we can easily find out the number of poles. So for AC machines, there is no problem in finding out the number of poles because we already knew what is the value of frequency and what is the value of speed. But in case of a DC machine, there is no formula like this to find out the number of poles. So we have to decide the number of poles considering few number of factors. Listed here are the few depending factors for selection of the number of poles for a DC machine. So in case of designing a DC machine, when you are about to find out the number of poles, you have to keep in mind all these factors in such a way the machine efficiency should not get affected in any format. So let us discuss what is each this depending factor tells us in the choice of number of poles. The first one is frequency. You might have a question, how this frequency comes in case of a DC machine? I hope you remembered in, in the armature, the nature of the voltage waveform which is generated is AC in nature. So there it happens because of the reversal of magnetism. So here the frequency refers to the frequency of the magnetic reversal. So how to find out the number of poles? Should we choose the number of poles to be a larger value or should we go for a smaller number of poles? Say for example, if I'm going for a larger number of poles, I am selecting a larger number of poles. Here we mean, suppose we have a choice between 2-pole machine and 4-pole machine. We are going for 4-pole machine, meaning we are preferring larger number of poles. So if I increase the number of poles, what happens? If I increase the number of poles, the magnetic reversal also will increases. Obviously, the frequency will also get increased. But we have to keep in mind, though the frequency increases, it should not exceed a particular range. Say for example, the frequency of the reversal should lie between 25 to 50 Hertz. So only if this frequency lies between this range, there won't be any problem. So while deciding the number of poles, you can go for larger number of poles, but you have to keep in mind that the frequency range should not exceed 25 to 50 Hertz. Next, we shall see these three factors one by one in the coming slides. The next factor is weight of the iron parts. What does the choice of a number of poles has relation with the weight of the iron parts? Okay, here we are seeing two different machines. The first machine is a two-pole machine. You have poles here. Okay, this is pole 1 and this is pole number 2. So you have two poles here, so we are calling it as a two-pole machine, and you have four poles here, we are calling it as four-pole machine. So in this case, just observe what is the nature of flux happening here. So if you compare these two machines, say for example, I am assuming the total flux around the air gap as phi. So if I take phi as the total flux, so in this machine there are two poles. So what will be the total flux per pole? That means ஒரு போலுக்கு கீழே எவ்வளவு flux இருக்கும் அப்படிங்கறத பார்க்க போறோம். If we are assuming the total flux as phi, since we have two poles here, so the flux per pole will be phi by 2. In this case, the flux per pole will be phi divided by 4 because the number of poles here is 4. Next, if the flux per pole is phi by 2, what about the flux in the yoke and the armature core? Say for example, just have a look at it. So here in this, this is your pole. So in this area, you have flux as 5 divided by 2. Now this 5 by 2 will be passing through this portion, as well as this portion. So what happens is this is nothing but your yoke, correct? So this is your yoke and you have an armature here. So what is the flux distribution over this area and this area? If you see, this flux per pole 5 by 2 is getting half over this portion as well as this portion. So what happens that this 5 by 2 becomes here 5 by 4 as well as here 5 by 4. So the flux in the yoke will be half of the flux per pole. Similarly, in case of your 4-pole machine, since the flux per pole is 5 by 4, the flux in the yoke and armature core will be half of it, that is 5 by 4 divided by 2, that is nothing but 5 by 8. So what do we infer from this flux distribution? So in case of a two-pole machine, okay, if you are using a two-pole machine, the flux in the yoke is only 5 by 4. If you go for a 4-pole machine, the flux in the yoke is 5 divided by 8. Okay, so when you compare these two values, what did you infer? So with increase in the number of poles, okay, with increase in number of poles, the flux in the yoke is getting decreased. That means the amount of flux which has to be carried by the yoke is getting reduced with increase in number of poles. So if the yoke has only less role in carrying out the flux, means the amount of iron spent for building the yoke will get reduced. So what happens is, indirectly, with large number of poles, the cross section of the area of the yoke gets reduced. That means the iron parts used will be getting reduced. So with increase in number of poles, the total weight of the iron parts gets reduced. So what is going to give you an increase in the cost economical efficiency, correct? This is one factor. The next factor is weight of the copper. Now here where we will be using the copper, here the copper means we mean the windings which are placed in your armature slots. So what they are saying is with the way what we are going to find it out, what happens if we increase the number of poles to the copper portion. Now this is case 1, okay, this portion is case 1 and this portion is case 2. In this case 1, there are two poles. This is first pole and second pole. So there are two poles. This is 2-pole machine and this is a 4-pole machine. Now these two dotted lines indicated means this line and this line indicates your armature. Okay, and you can see that this portion is nothing but the winding which is getting connected to a commutator segment. So this portion is the one. So this portion, that means the one. This portion is the actual conductor which is lying in your slots, and this conductor portion is nothing but which is lying outside the slot. Okay, so usually we will always call the copper winding present in the slot as the actual copper or active copper, and the copper winding portion which is lying outside the slot, that means here we'll call this height as overhang. Okay, if the we'll be calling this portion of the copper conductor as inactive copper. Clear? So this portion is active copper and this portion is inactive copper. Now what inactive copper means, the usage of, that copper is actually getting wasted there. Okay, the property of the copper is not used completely. That is why we are calling it as inactive copper. But in case of the copper winding which is lying in the slots, that is solely responsible for producing your EMF and current. So that we are using the full property of copper there. So we are calling that as an active copper. I hope you are clear with the two things. One is active copper, another one is inactive copper. Now what happens if I increase the number of poles? Now if you see here, you have 2-pole machine here, and if you have a 4-pole machine, you can see that when you compare these two, the overhang is getting reduced here. Clear? This overhang is getting reduced. That means the amount of inactive copper is getting reduced with increase in number of poles. So if the amount of inactive copper is getting reduced, means we are actually using the available copper winding in a proper way. So that is very good from the economical point of view. And also the copper loss also will be getting reduced, and the weight of the copper also will be getting reduced with increase in number of poles. So from this we can understand that if we go for a large number of poles, okay, the weight of the copper will be getting reduced on a whole. The next factor is length of the commutator. Let's see what does this selection of number of poles has to do with your commutator length. Okay. Now again we'll take a comparison of two pole machine and a four pole machine. Here you have two poles here, 1 and 2. Here you have four poles, 1, 2, 3, 4. Now this is nothing but the brush arrangement. I hope you know what is this. You will be having a commutator segment fixed to your shaft, and we'll be usually denoting this as a brush. So this is your brush, and you know that only through this way the current is carried over to your external circuit. Okay. Now in this case of two pole machine, say for example, this current is getting passing like this. Okay, I'm assuming that this current is circulating like this, and I'm naming it as IA. So what happens is this IA, when it comes here, so they are having two parallel paths. I hope you know what is meant by parallel path. So what happens when this current increase in when the current enters to this brush portion, this will be a portion of the current will be passing through this side, and the remaining portion will be passing through this side. This is what we are calling as parallel paths. So this IA will be flowing it as IA by 2 and IA by 2, and in this portion again they will become a common point, and this that IA by 2 plus IA by 2 becomes IA here. Okay. Now if I increase the number of poles, what happens? The brush arms also will be getting increased. So if the brush arm is getting increased, that means the number of brush arm is getting increased means the parallel path current also will be getting decreased proportionally. Say we'll take this example. You have four poles here and you have brush sets, two brush pairs. Okay. Now assume that these 2 points are connected together, this brush as well as this one. Okay. So this IA input current is getting flowing like this. It is going as IA by 2 here and is going it as IA by 2 here. Clear? So since this is IA by 2, there will be two parallel paths here. I mean, one parallel path like IA by 4 and IA by 4, because the incoming current is IA by 2, that will get halved again. So it will be IA by 4 and IA by 4. Again, this IA by 2 will be getting halved as IA by 4 and IA by 4. So again, these two will be joining here. Okay. And that will be going it as IA by 2. That is IA by 4 plus IA by 4 equal to IA by 2. Clear? Right. So what is the inference we are going to get from this? Now, if you are consider two pole machine, what is the current carried by this brush? The current carried by brush here is it is IA. Okay. Now, if you are going for a four pole machine, the current carried by each brush is IA divided by 2. Okay, so let us compare these two currents. So if you are having we'll take this two pole machine as a low number of poles and four pole machine as a higher number of poles for comparative purpose. So if I increase the number of poles, okay, if I increase the number of poles from two poles to four poles, what happens? The current carried by the brush is getting decreased. That is, here it is IA and here the brush current is IA by 2. That means the brush current, with increase in the number of poles, the brush current is getting reduced. If the brush current is getting reduced means the resistance is higher. That means R equal to rho L by A. So if R is high, A is less. That means when you compare the first and the last portion, you can see that with increase in the number of poles, there is a decrease in the brush current. If there is a decrease in the brush current means the area is also getting reduced. If the area of the brush is less, obviously the commutator length will be less because the brush is going to rest upon a commutator. So since the brush area is becoming less, the length of the commutator also will be less. Okay, suppose if the brush area is more, in order to hold the brush area and its setup, the length of the commutator should be more. So what do we finally find it out here is, with increase in number of poles, the length of the commutator is getting reduced. What is the use of getting a lower getting a uh, lower value for the length of the commutator? If the commutator length is less, obviously the cost involved in manufacturing this commutator will also be getting reduced. Next, we will go for this factor, and finally we'll go to these two factors. Okay. So next we'll see this depending factor called distortion of field form. So, what do you mean by the distortion of field form? Okay, we all know that the armature MMF, we know AT indicates the MMF, and armature MMF means I'm representing it as armature MMF as AT suffix A. The armature MMF per pole is having a formula like this as AC divided by 2 into the pole pitch. So what does that mean? It is AC. You know what is AC? It's nothing but specific electrical loading. It is AC divided by 2 into tau is nothing but pole pitch, which contains pi d divided by p. So what do we infer from this? So we can compare that the armature MMF per pole ATA is inversely proportional to pole. That means if you choose a lower value of pole, that means if I choose a lower number of poles, what happens if I choose p value as less? So by this expression, the armature MMF per pole will be more. That means the magnetizing MMF per pole will be more. If this value is more, obviously the flux distortion will be higher. Okay, so if flux distortion is higher, correspondingly, you can see that there will be so more number of problems, especially commutation losses. Commutation losses means here we mean that the sparking problem. So automatically the efficiency will be poor. But so what did we again I repeat, if the number of pole if you choose the number of pole as a lower value, then your ATA value will be higher. That means the flux distortion will be more, leading to losses. So in order to avoid this distortion, you have to choose a large number of poles as the final answer. Next, we'll go to the flashover. So what do you mean by flashover? I hope you remember that due to the presence of a commutator and the brush setter, the common problem which you'll face in DC machine is sparking. So if we go for larger number of poles, say we'll take this diagram. If we go for larger number of poles, so compare these two diagrams. Here with low number of poles, you have only two brushes like this. Here with the more number of poles, you have four brushes like this. So with larger number of poles, the distance between the two brushes are getting reduced. See here, the distance is more between these two brushes. Here, the distance between these two brushes are less. So with the reduction of the brushes, suppose you have a spark produced here, and spark produced here and here. So there is a chance like all the spark might get connected in the air, and that is what we'll call it as a flashover. So far we have seen the advantages of having larger number of poles. Now we are seeing the first disadvantage, that is with increase in number of poles, there is a chance of flashover to occur. And the last one is your labor charges. That is very obvious. Suppose if you are going for a large number of poles, then you require more number of windings which has to be wound around your poles. So those things require more labor work. So we have to pay the labor their charges. So automatically the labor charges will be more when we go for a large number of poles. So we have come to the last portion of our today's topic. So let us to summarize all the points we have discussed so far. If you are going to decide the number of poles for a DC machine, you have to keep in mind about all these depending factors. Suppose if you are going for a large number of poles, that means if you are selecting a larger number of poles as the final value, what are the advantages you will get are the weight of the iron parts will be reduced, the weight of the copper will be getting reduced, length of the commutator will be reduced, then distortion of the field form also will be getting reduced. So these are the benefits if you go for a larger number of poles. But at the same time, with a larger number of poles, you will face the problem of flashover and high amount of labor charges. And you should also keep in mind the frequency of the magnetic reversal should not exceed the range. So, this is not an algorithm or a step-by-step design procedure to choose a number of poles directly. So, we have discussed only the factors which are connected with the selection of number of poles. So, you have to keep in mind with all these factors, and you have to decide an optimal value for the number of poles. Thank you.